In this video we will discuss about moving coil galvanometer. So in last video I told you about how torque is experienced on a coil which is carrying current and which is kept in a magnetic field. So this was the principle of this moving coil galvanometer. That means the moving coil galvanometer, it has a principle, and the principle is that moving coil galvanometer is based on the fact that when current carrying loop, that means that rectangular coil, is placed in a magnetic field, uniform magnetic field, it experiences torque. This is the principle. Okay, so galvanometer means basically it is the you can say instrument which measures, which detects the presence of current in a circuit. It does not measure anything, it just detects whether current is present in a circuit or not. Okay, so from outside a galvanometer looks like a voltmeter or ammeter. You have seen the voltmeter and ammeter, right? From outside it looks like that only. It has this type of scale. There is a zero reading. This side also we have this kind of scales. This side also you have. Okay, then there we have a pointer like this. When this pointer it remains at 0, then we say that, and in this galvanometer there will be two terminal, positive negative it is written, written, or it is one is red in color, one is black in color. So these two terminals are connected to the main circuit. So when current flows through the main circuit, that current also flows through the galvanometer, and this pointer it shows deflection. It goes this side from 0 or maybe this side from 0. So if when it shows deflection, we can say that in the circuit there is current. Okay, now under on which principle this galvanometer is working? There is a principle when a coil is placed in a magnetic field, it shows torque. Okay, now the construction of galvanometer is like this. So here you can see there is a phosphor bronze strip, this one. With that there is a mirror. What is the function of the mirror? That one I will tell you later. This is the rectangular coil. Here you can see that this rectangular coil is having many turns. 1 turn, 2, 3, in that way it has many turns. That means suppose it has n number of turns. Then inside this rectangular coil there is a you can say material. This material is generally, it is made of soft iron. Somewhere it is written, just a second. Okay, yeah, this one. A soft iron core is placed within the frame of the coil, this part. Okay, now see what is the purpose of this soft iron. It provides more permeability, because instead of soft iron, if you keep like air medium, in that case permeability will be mu naught. If you keep soft iron, the permeability will be more than that, so the effect of magnetism will be more there. So that is why soft iron core is used there. Anyways, then what happened is there are two magnet, north pole, south pole, and if you remember in last class I told you that the shape of the magnet is concave shaped. That means these are forming a radial magnetic field. And what is the purpose of radial magnetic field? It always makes that theta angle 90 degree. Okay, and as a result the tau in the circuit will be the maximum torque. How much is torque then? NIAB, right? Now this one you can see, as I just now I told you that in this galvanometer there will be two terminal, right? So that two terminals are this one T1 T2. Okay, so T1 and T2 are the two terminals. See, when these two are connected to the main circuit, current enters in the galvanometer through any one of the terminal, maybe suppose through this terminal, then current comes like this, then then through this side it goes like this, then through the spring it enters in the coil. In the coil it goes on, it just takes some turns, and then it goes like this, and through this turn it goes out current. Okay, or if current enters through this side, then it will go like this one, then it will enter in the coil, it will uh, make the coil rotate, because when current starts flowing through the coil, already radial magnetic field is there, so this coil will experience a torque, and due to that torque this coil will rotate. And just now I told you that if galvanometer is like this, there is a zero, the pointer is there, this pointer is actually attached with this part of the galvanometer, that means with the coil there will be one pointer, there will be a scale like this. Okay, as the coil rotates, when current enters in the coil gets the torque and it rotates. Along with that, this pointer also rotates. It goes this side or it goes this side. Okay, and when we can this thing is wholly inside the instrument, so this thing we cannot see. What we can see is we can only see the pointer. The pointer is moving. Pointer is moving means there is current in the circuit. Okay. Now, two things you remember. What is the purpose of this radial magnetic field? And uh, theory. Next is the theory. This one. So, in theory, we know that the torque is this one. Okay. So, if this is the torque, due to this torque, what happened is this phosphor bronze strip, this part, it also undergo, or it will also be twisted, because the coil is rotating. The coil is rotating, so this strip will also be twisted. The spring here, it will also twist by little amount. Okay, now say when the current is withdrawn, when current was present in the galvanometer, then it shows deflection, it get this phosphor bronze strip, the spring along with the coil, it also undergo, or it also be twisted. Okay, now when the current is withdrawn, then this phosphor bronze strip or the spring both has to come to their initial state. So when they will come back to their initial state, what thing will be responsible for this coming back of initial state? That is called the restoring couple, just like restoring force. I think you remember, like if there is a spring, if the spring is stretched with some force, we call it applied force. When this applied force is withdrawn, then the spring again comes back to its original position or state by applying a backward force. We call it the restoring force, and the amount of this restoring force and the applied force are equal. Same case will happen here also. What is the applied torque? This is the applied torque. What is the restoring torque? Restoring torque means the torque which is bringing the whole system again in the original state. So that restoring torque is, suppose, k phi. Why k phi? K phi means, here you can see what is k. K is the restoring torque per unit twist. Just a second. Yeah, k is the restoring torque per unit twist. That means per this phosphor bronze and this spring, they are getting twisted, right? Suppose for 1 degree twisting, how much is the restoring couple associated or restoring torque associated? That is the k. Okay, so for 5 degree twisting, how much restoring torque will be associated? K into 5. So this is the restoring torque which will be equal to the applied torque. So that's why we got this formula. NIAB should be equal to K phi. What is phi? Phi is the restoring torque per unit twist, and what is K is the restoring torque per unit twist, and what is phi? Phi is the total amount of twist in terms of angle. Phi is what? It is the deflection or total amount of twist we can see. So we can write this one, applied torque equal to restoring torque. Okay, from this we can write this I. Now here this term k by NAB, this has a specific name, we call it galvanometer constant. so which is given by G. So we can write it like this: I equals to G phi, and if G is removed, then I is proportional to phi. Okay, G is the galvanometer constant. Now this is the theory, or this is the formula that we can get from this moving coil galvanometer. Another thing I already told you about this mirror, no? What is the function of this mirror? See, basically the galvanometer that we use, there instead of this mirror we have a pointer. Already I told you about it. But there are some galvanometer where the reading is taken with the help of this mirror. How? Suppose here the mirror is there, there is a source of light. Suppose a lamp or any source of light, and there is a scale like this. This light ray, it falls on the mirror. Mirror reflects the light ray. It reaches somewhere here, suppose, when no current is in the circuit. As the current starts flowing through this coil, then what will happen? Then this phosphor bronze strip will get twisted along with the mirror, and now the light ray will fall, but the mirror has got twisted. It may reflect the light beam maybe somewhere here. Initially the light beam was here, now the light beam is here. So by observing the shift of light beam, we can say that current is flowing through the galvanometer, or the galvanometer will be able to measure the presence of current, or it will be able to detect the presence of current in a circuit with the lamp and scale arrangement. So this mirror is required for lamp and scale arrangement. Okay, where there will be a lamp and there will be a scale also. So I think this part is clear. Then sensitivity of galvanometer. Okay, this part also you remember, this part, radial magnetic field, it is written here. A radial magnetic field produced by a concave shaped pole of permanent magnet of galvanometer is always parallel to the plane of the coil. Parallel, why they have written? Because see what I said, that the okay, the coil was like this, no? The coil was like this. N cap, the perpendicular was somewhere here, that was N cap. The magnetic field B was like this, and this was our angle theta. Okay, so this theta, what we said, that for radial magnetic field this theta should be 90 degree. If theta is 90 degree, this is the angle by the perpendicular of the surface. So theta is 90 degree, that means can we say that the plane, I mean this plane, okay, and this one, this magnetic field, they are parallel. Can we say theta 90 means how will be the orientation of the coil? The coil will be like this. This will be the orientation of the coil. This will be beta, I mean B, magnetic field. Okay, that means the magnetic field is along the plane. So that's what is written here. What is given, that always parallel. There they are saying it is parallel, but what we say, that the angle is 90 degree, because we are measuring the angle not with the plane but with the perpendicular of the plane. Okay, so if the perpendicular of the plane is making 90 degree angle with B, that means what, the plane of the coil is parallel to B. I hope it is clear, right? The perpendicular of the coil, it has made 90 degree angle with the magnetic field. That means the plane of the coil, this plane, it is parallel to B. That's what is written here. Instead of that, if you write that the normal of the plane makes 90 degree angle with the magnetic field for radial field, then also it is okay, fine. All right. Then next is sensitivity of galvanometer. Two types of sensitivity you will get: current sensitivity and voltage sensitivity. You just have to remember the formula. Current sensitivity means it is phi by I. So phi by I, if you do from here, phi, this one, phi divided by I, what it should be? It will be reciprocal of G, that means NAB by K. That's what is written. This is the current sensitivity of a galvanometer. So it is written that the current sensitivity of a galvanometer is defined as the deflection produced in the coil of the galvanometer per unit current through it. Yes, there is deflection per unit current only. Deflection means phi per unit current. So the value comes as this. This is the current sensitivity. Voltage sensitivity means phi by voltage. Current sensitivity phi by current, voltage sensitivity phi by voltage. So now we know from Ohm's law V equals to IR. Substitute it. Okay. Then phi by I, this value already we got NIAB by K. Just extra is R here. So R will remain as it is. Okay. So this is the voltage sensitivity. Alright. Now in next video we will discuss this part. That will be the last topic of this chapter, that is conversion of galvanometer into ammeter and conversion of galvanometer into voltmeter.